So for the eighth and the last live session, or the last week of content that we have for the course, we will be dealing with the Aeolian geomorphology. So Aeolian, actually the term Aeolian comes from the Greek god of winds, Aeolus. Okay, so that's where we get Aeolian, the term, and the Aeolian geomorphology is the study of geomorphic processes as well as the geomorphic landforms that are formed due to the action of wind. Okay, so as it's mentioned over here, so Aeolian landforms which are formed due to the erosional, transportational and the depositional action or processes carried out by the winds. Okay, so usually these form in the action of wind is not very prominent in areas where the wind faces a lot of obstacles in its path. So it needs a large area where the wind can blow over the surface of the earth without much hindrances. So where the wind itself can gain very high velocity for it to carry the amount of sediments with it, or at least shape the already occurring features. Maybe there's a rock that is protruding from the earth's surface, and it gets eroded by abrasion by the sediments that are carried by the wind. Okay, so for the abrasion to happen at a rate where it can actually change the feature itself, the wind velocity has to be much higher. So these kind of landforms are not seen all across the globe. Okay, so there are certain environments where the action of wind is more prominent. Hence, the Aeolian geomorphology that we wish to study also are associated with such environments. So few examples of such environments are the coastal zone. While in coastal zone we have seen that the action of wave is prominent, but when it comes to the formation of, say, beaches or beach dunes that as we had seen in the last week, the wind itself also plays an important role. So like during summertime, the winds can actually carry a lot of sediments along with it, and it can shape up the dunes that are present in the coastal zone. So in the coastal zone, while there are features which are dominantly formed by the wave action, some features also have some like the causes of the formation of few features in the coastal zone can be due to the wind. And the next environment that are more common, and where mostly we focus our understanding of the Aeolian geomorphology are the deserts. Okay, so you can have cold and hot deserts. So cold deserts are usually found in high altitude regions where you have very low temperatures. Okay, so you can have cold deserts. Okay, so the characterization of an area as a cold desert mostly entails low temperatures, okay, high altitudes, very low or almost absent precipitation in these areas. Since there is no precipitation, so mostly it is precipitation. So mostly these areas are arid in terms of the humid conditions over there. So there are no humid conditions, there is not much moisture present here, But since these areas have very low temperatures and usually situated at high altitudes, so hence these can be termed as cold deserts. So, for example, in India, Ladakh is said to be one of the examples of cold deserts. And then we come to hot deserts. Now, hot deserts, obviously, these are mostly typically located in tropical and subtropical areas, and you will mostly find them occurring in rain shadow regions. We will see in upcoming slides what are rain shadow regions. So obviously they have a higher annual temperature or the mean annual temperature of these areas is pretty high. There is another characteristic that we will see, that in hot deserts your day and night temperatures vary a lot. There is a high diurnal temperature variation also in hot deserts, and mostly the air over here is very not warm, but it's hot, and moisture content obviously is going to be lower, and since it falls in the rain shadow regions, they also have very low moisture. The winds that are actually blowing over this over the hot desert area. So obviously we have examples of hot deserts in terms of Thar as well as Gobi deserts. And then another environment are the agricultural fields. Sorry. Okay. So agricultural fields. Now agricultural fields is obviously the the region, the fields itself are, you can call them as, man-made landscapes, because obviously we denote the areas where we would want to maintain the agricultural lands. But since these have very large expanses in areas, and if they are not vegetated, or if there are a lot of you know sediment supplies present over there, also when the winds are blowing past these areas at a considerate amount of with considerate speed, then you can see some sort of wind related geomorphic features in these areas also. But mostly for the sake of for ease of understanding, and also because we know that hot deserts are the areas where we have more sand supply, also sand silt sediment supply. So we will be seeing all the different kind of geomorphic landforms that are created by winds in hot deserts. So some of the criteria that needs to be met, as I had also said in the when we were talking about the different environments, almost non-existent vegetation cover would be there, because if there are vegetation, obviously the wind is going to face obstruction in its path, and then it won't not move on. And there needs to be ample amount of fine sediment supply, so mostly clay, silt, sand, as these can be, we will see further that these can be very easily carried by the wind in form of kind of suspended load. And some of the examples of the geomorphic features that we will see are obviously sand dunes. Whenever we picturize a desert, we always are shown in different type of visual aids, kind of sand ridges, and so these are mostly ridges and sand dunes. Then you have lowest deposits, ventifact, yardungs, deflation hollow, blowout, desert pavement. These are some of the common examples that are associated with aeolian geomorphic processes. So before we move on to the the action of the wind per se, let's first see which areas are mostly considered to be deserts. So across the globe, 1/3 of the Earth's surface is actually classified as arid land, desert, and obviously, as I said before, they can be hot as well as cold. And you can have extremely arid areas which are deserts, or you can have arid deserts, and then you have some grasslands which actually come in the classification of semi-arid, and these are called steppes. So mostly the wind, the aeolian geomorphology that we see mostly, fall in the arid and semi-arid or extremely arid land. So as you can see in the diagram over here, you have extremely arid, arid and semi-arid regions marked, and you can see that extremely arid lands are mostly the Sahara, and then you have some part of the uh, Arabian Peninsula over here. Then you have arid lands, so you can see that the Thar Desert area, that is a part of India, actually comes in the arid land. And then you have semi-arid land, so where you have the mean annual precipitation is slightly higher than the extremely arid and the arid lands. So there we have three categories, and obviously the aridity that is present in a land is is classified according to the amount of precipitation that is received by the area over there. So now let's see how a desert actually forms. So as I had mentioned the term rain shadow region, so that is a very important uh, phenomena that actually, excuse me, yeah, so that actually uh, makes, or that helps in the desert formation. So let us see from the how precipitation plays a role in the formation of the desert. So as we know that with evaporation that happens over the water surface, so that creates the clouds, and the clouds move inland, okay, towards the mainland. Suppose if we are taking India as an example, so most of the southwestern, the monsoon winds that are there, that blow inland, and when they are actually coming towards the mainland, so you have the orographic precipitation is what actually plays a role in the monsoon rains that we have. So in that, the warm and moist air actually moves upwards when it comes in the in contact with mountain ranges, and as the warm moist air rises upwards, it actually expands and cools. And since the colder air is it cannot contain the amount of moisture that the warm air actually had brought in with it, the water obviously starts condensing, and then we get the either in terms of rain or snow, the precipitation. So this is known as the orographic precipitation, and as you can see, so this is the upwind direction, okay, since the wind is blowing from your left side to the right side. So this is the upwind directions, and this is your downwind direction, okay. So mostly you will have all the vegetation, as you can see, all the precipitation is happening in the upwind side, and this area is where you have most of the vegetation present. So most of the moisture is now already precipitated out in the upwind direction. So now the clouds which are devoid of the moisture, and it is also become cooler in temperature since it has reached a higher altitude, but since the moisture is not there, it is drier now, and it will move towards the other side of the mountain. Now as it moves towards the other side of the mountain, it starts warming up, and because it has warmed up again, it starts descending. Now this the downwind side, okay, so this is your upwind side and this is your downwind side. So the downwind side now does not have any air which contains any moisture. So if there is no moisture, you have no clouds, and hence this area then becomes your dry, it can be specifically called said to be dry land, since the clouds no more have no moisture. Okay, so no moisture in the clouds, so you have no precipitation, no precipitation. Okay, so this area is called the rain shadow region. So this is called the rain shadow region. Now in this rain shadow region, obviously since we have no moisture and the even if there is any amount of moisture present, the precipitation, the amount of rainfall is going to be very low. Okay, so very low rainfall. As you can see, if it is mostly below 250 millimeter per year. Okay, and since there is since there is loss of moisture and very low precipitation, vegetation is not supported in these areas, and if there is no vegetation present over there, any kind of sediment like soil or clay or silt, even rocks for that matter, rock fragments, they are open to the erosive activities that will be done by the winds in this region. So hence, if the all the smaller particle size sediments are present in these areas, they will be carried ahead by the wind. Now since there is no obstruction like vegetation, and what you are left with are just sand and rocks, and what you have is a very either rocky terrain or a dry area. So there is no humidity at all, and since there is no humidity, the sun in these areas is actually very harsh. And as I said before, the deserts or the hot deserts have very high range of variability in the temperatures that we observe in the day and in the night in such areas. So this is how the desert is formed due to the whole phenomena of orographic precipitation and the rain shadow effect that we have. So now we see that we have got an environment where wind activity is very prominent, and it can erode, transport and deposit the sediments. We will see some aspects of wind which actually causes it to function as this natural agent which is creating different landforms and landscapes. So wind is obviously it's a moving mass of air, and this mass of air is moving because of temperature differences, pressure differences. So this is the driving force that is behind the difference in the pressures in two regions. And obviously this has an the underlying effect is the also the content of moisture that is present in the air that is moving. So greater the pressure gradient, the greater is the driving force for the air in the wind, and if that is exceeding a certain point, the wind speed increases. Okay, so the wind speed is directly proportional to the pressure gradient that is present between the two regions between which the wind is actually passing through. And for the we have seen that river you know though fluvial geomorphology or fluvial geomorphic features are more abundant on the earth, wind has more capacity of erosion and transportation. Okay, so because you can imagine that while the river is flowing, it has to maintain a course. Okay, and it can only erode and transport uh, between the boundaries of its river banks. It can expand a little, but it cannot have the activity of erosion and transportation cannot go beyond a certain beyond a certain land expanse. But that is not the case for the wind. if there is a huge amount of a huge area that is present which has no obstruction, and the wind speed is enough to carry the material with it, the wind can cause very high level of erosion, where all the small sediment particles can be just blown off from that area, and what you are left with is just a dry rocky terrain. So this is possible because wind is one of the greatest agents of land erosion and transportation. So this is mostly, as we have seen, is more effective in extremely arid regions as well as some semi-arid regions. And because of the hot temperatures that we have seen, because the sun is harsher in these areas, your air or the wind that is blowing over this this particular area is always going to be very high in temperature. And since the air near the earth surface is automatically heated, it will rise, and the cooler air from the region, due to the pressure difference that is there, will replace this hot rising air. And this is where the generation of winds, as we said, the driving force is the movement due to the pressure differences. If the pressure gradient is high, this replacement of the cooler the replacement of the hot rising air by the cooler air is going to go on at a higher rate, and it can create or generate very strong winds. And if the winds are very strong, it can erode and transport sediments on its own. And wherever these winds actually face a barrier or an obstacle in its course, or by because of natural causes, if the wind speed decreases, it can deposit them over a large area. So because this area is obviously very hot and has no moisture, the soil over here that is present over here, mostly you will have a rocky terrain, barren terrain in these areas, but if there is soil present, it has very little moisture. And since the soil does not have any moisture, it cannot adhere to any of the rock fragments or any of the sediments that are present over there. So it's very easy for the sediments in these areas to be blown away by by the highly uh, you know uh, the the winds that are generated with very high speed in these areas. So as we said, that since wind can erode at a very high rate, so the primary two factors that are there are the wind velocity and the surface roughness. So if the obviously, as if the wind velocity increases, your erosive force will also increase. If obviously, if the wind speed is not that high, it cannot carry the larger sediment grains, which can cause the erosion of the other surfaces that are present over there. So fast winds can cause much more erosion than slow winds. So this is how it goes. Now roughness of the surface has a role to play. If if the friction is increased, if there are more obstructions, or there are more surfaces that the wind has to blow over, the frictional force, that is the resistive force that is present over there due to these features, actually can reduce the wind velocity, and then you will not have that high an erosive action that what it would be if there were no such features present. If there is only sand that is present over there, it is very easy for the high velocity winds to just carry it from one place to another. But if there are rocks in between, so obviously it is going to face an obstacle, and it can reduce the speed of the wind. Now the few of the erosive processes that the wind carries out, they can be called as deflation and abrasion. These are two most important erosive processes that happen with respect to wind erosion. So in deflation, what happens is there are fragments of rocks that are present, and also there are fine sediments like silt, sand, dried soil, and clay. Okay, so in deflation, these smaller sediments, okay, these finer sediments are actually blown away by the sand, and the wind speed is so great that some of the rock fragments also get scattered from the area where these are actually all settled. So the blowing wind first carries away all the fine grained material, and what is left behind are the coarser fragments. Okay, so this is when I was saying that you can form areas which are rocky, as well as you have only rock fragments and uh, rock exposures that are present, because all the finer grained sediments have been blown away by the deflation action. Then what you are left with behind are called rocky deserts. Okay, so rocky deserts are essentially formed by the action of deflation. Then the next erosive or erosional process that is associated with winds is called abrasion. Now abrasion is easy to understand, that anything that is scratching the surface, anything that scratches the surface is actually the phenomena of abrasion. So that's what it is. So mechanical scraping of a rock surface. This is caused due to the friction between the rocks and the moving sediment particles that are being carried by the wind. So if there is a rock exposure and the wind itself is carrying some finer rock fragments with it, so it can scratch the surface of the bigger rock exposure, and due to abrasion the rock exposure can get shaped into a different kind of a feature. So this also has sometimes what we have something called a mushroom rock. Okay, so first this used to be a normal rock fragment or rock exposure. Okay, so due to the smaller particles that are being carried by the wind, actually abrades, or it starts eroding the sides of the uh, exposure. And then what you are left with, if like this is of a great height, the rock exposure itself is of a great height, and the wind actually is not reaching the top of the rock exposure, it is only going towards the the lower half of the rock exposure. So the bottom part of this rock exposure actually gets eroded from all sides, and what you are left with is like a mushroom shaped rock feature. Okay, so you can have mushroom kind of a rocks features. So this is kind of what can be formed due to the abrasion action. Now another process is called corrosion. So this is obviously this can groove and scar and also polish the surface of the rocks. This might not erode the entire rock feature. So suppose this is your rock exposure, okay, and this part is getting hit by the different kind of the sediment particles. So this part actually with time gets more polished, okay, or it can show different kinds of grooves depending on its the angle that it is creating, and the angle at which the sediments are actually hitting the surface of this rock exposure. So these are some of the erosional um, processes that are associated with winds. So some features that develop due to large scale erosive processes, erosional processes by the wind, are called deflation basins or blowouts. So these are hollow depressions where the finer sediment or the entire area is actually made up of finer sediment particles itself, but due to the wind, a hollow depression is created, because on the surface all these finer grain sediments have been carried off by the wind. And then you can have if the hollow actually cuts the groundwater table, or it actually reaches the contact between the aquifer and the top layers, so you can have small kind of lakes, so swamps or oases can be formed due in the deflation basins that are created. So, and the other one where we were talking about the rocky deserts being formed, there is another feature called desert pavement. So, this has the similar deflation phenomena where the finer sediments are actually carried off by the wind, and what you are left with are rock fragments. And with the removal of the finer sediments, the surface, the level of the surface also gets eroded away, and then the surface actually falls down. This is how you can also have another hollowed out kind of a feature over here. But mostly later on, if there is no more sediment grains, finer sediment grains that can be carried off by the wind, what you are left with is only the different rock fragments that are present, and what you get, what forms then is called the desert pavement. Okay, so you can see, so it's mostly removal of fine grain particles, and the concentration of coarser grain particles increases, and the surface only has coarser grain fragments, and it is called a desert pavement. Now, another aspect, which has a little bit of chemical erosional process also involved. So, that is when the during the development of desert varnish. So, what happens is that rock surface actually gets a dark shiny stain, which is mostly made up of manganese, iron oxides, hydroxides and clay minerals. So, these actually form a thin layer on the rock surface, and this is when the surfaces of these rocks are actually exposed for a certain time of for a certain period of time, and the minerals that are already present in the rock, with the differences in the temperatures and the continuous abrasion that happens, there is a chemical reaction that also takes place, which forms a sort of a layer of this stain, so which is actually called desert varnish, or you can also call it rock varnish. Now, another few features that are formed during the erosional part of the wind geomorphic processes. So, one of them is called ventifacts. Now, ventifacts is an example of how abrasion actually changes the appearance of the rocks or the landscape that is present. So, these are actually rocks which have been abraded, pitted, or you can find grooves and scars on the surface of the rock. Sometimes these get highly polished if it is continuously bombarded and affected by finer sediments. Okay, so the abrasive action is very high during the formation of ventifact. You can see that this entire area actually gets eroded off and abraded off, and now you have a plain polished surface. So, ventifacts, if they are present, so mostly you can say that wind action has been very dominant in this area. Now, yardang is another feature that we see in areas where the erosion carried out by winds is very it's high. So, these are actually parallel kind of hills you can see over here, and these are parallel to the wind direction. So the suppose this is actually a harder rock that is present, and there are softer material kind of lining side by side with these hard rock material. So this soft rock or the less resistant rock is actually eroded much more easily compared to the harder rocks, and so what you are left with are these kind of elevated ridges of the hard resistant rock, and these troughs are found where you have the softer rocks. So these are actually called yar dungs. So this can they can go for kilometers long, and mostly they are shaped by the winds, and they will be forming parallel to the wind direction. Now, Zeugin, as I had kind of given you example of the mushroom rock that we saw in a few 2 slides before. A Zeugin is also another such kind of a feature that are formed. Now, the top surface of the Zeugin is a tabular mass, and you can see that this is actually been shaped by the winds that have been going okay, that have been flowing in this direction, and you have alternating layers of hard and soft rock. So the layers which have the soft rock is actually eroded much faster compared to the harder rock. So this is the harder strata and this is the softer strata. Okay, so you can see that how the resistance to the erosion done by the winds can actually affect the formation and the structure and geometry of the features that we see. Now we saw how the erosional processes play a role and how different features are formed. Just excuse me. So now we will see how the sediments are being transported by the wind. Now, during erosion, we saw that some rock fragments and fine grained sediments are carried off, but each of them, the power of the wind to transport each of these different particle sizes differs. Uh, you need a very high velocity of the wind to be for it to be able to transport larger fragments of rocks. Okay, because it is difficult for the wind to carry the larger sediments with itself, but all the finer ones mostly they are carried with the wind by either we will see the different processes, but most of it is actually carried by the suspension. So you can have lift bar bombardment and drag. Okay, so this is these kind of processes or mechanisms are actually meant for eroding the mass. Now for the transportation, you can have, as I said, suspension. So very small particles are picked up and then they are carried by the wind and they are suspended in the wind that is there. The next the next transportation mechanism that is done or that is carried out by the wind is the saltation. So these are actually kind of hopping from one place to another. Okay, and these actually gain the energy to get transported when they are hit by a different kind of uh, by a different sediment. Okay, so where it gets the kinetic energy again to move with the wind, and repetition has where the hitting of a bigger sediment actually causes the kind of an it's a bombardment, and because of that bombardment actually finer sediments are created again due to the disintegration of the particle. So if to show in that manner, you can see that if this this sediment hits this grain on bombardment, what happens is that this grain scatters and forms a shower of smaller fragments. Now these fragments are actually going to hop about and being carried out in the wind in in the manner of saltation that happens. So these are kind of mostly saltation and reptation. Both of them have the bouncing of sediments from one place to another, and then you have the surface creep. So surface creep is for the larger rock fragments less than 0.25 sorry, greater than 0.25 millimeter, and these are actually kind of displaced from one place to another as being dragged on the ground surface itself. Okay, so if this particle hits this, so then this will get dragged forward, and it's similar to the saltation, but uh, the it does not gain a lot of height when it is moving from one place to another. It's mostly dragged on the surface, and it is pushed by the particles that hit it. So this is the kind of transportation mechanisms uh, that are active when the wind is transporting the different sediments. So uh, we saw how the wind erosion actually takes place, and also the transportation of sediments in itself also causes the erosion of the erosion that is happening on in the desert lands. So some of the factors which actually which will control the extent of erosion that is done by the wind is obviously the climatic situation at that point of time, the aridity. If there is moisture present, then the soil can hold on to the sediments that are present, and the wind itself will not be able to carry these sediments, or and if they cannot carry these sediments, then they will not get eroded. So soil texture, soil structure, again these are in the similar manner, state of the soil surface, the vegetation and soil moisture. So these are the factors which play a role in the intensity of the wind erosion that can happen. So desert environments, as we had seen before, so you need the features that actually characterize a desert environment is the very low annual rainfall and mostly devoid of vegetation. Then the diurnal variation and the annual range of temperatures that happen that are present in the desert environments are very high. The variation is very high. Then frequent occurrences of dust storms where the very fine sediments like sand, silt are actually transported from one place to another by the frequent dust storms that happen. Obviously that is also partly true because of the low moisture that is present in these lands, and obviously high velocity winds and dominance of sands. So these are also the factors that can either help in the geomorphic processes that are done by the wind or not. Then what are the some of the effects of wind erosion that we see? So as we said that the transport of small sized particles actually is the first thing that we see. The finer particles like if there is organic matter, clay and loam, so these can be carried from one place to another over very great distances, and this matter actually gets deposited in another area. So all the fertile matter can actually be just carried from one place to another, and the area where the wind velocity is much higher is devoid of these fertile elements that are required for the soil if we want to have agricultural lands present over there. So this alluvial matter actually is then uh, a, deposited in another area, where if this is if the span of this alluvial matter is much larger in nature, then it can form loess. So loess soils are those, it's actually very fertile, and it is due to this phenomena where the wind actually carries all the organic matter, clay, from one place to another place. And another important, you can say, landform building effect that we see due to wind erosion and transportation is the formation of dunes. So the mounds of sands that are actually forming these dunes actually can move from one place to another with the transportation effect of the wind. So we will see how they also, how the action of wind and the variation in the wind direction and the speed can change the geometry of different dunes. So, so now we have seen the erosional processes and the geomorphic features that are created by wind erosion. Then we saw the different kind of transportation mechanisms, and how the landscape is changed or modified due to the erosional and the transportational processes by the wind. Now we will see what happens when this when the sediment supply that is actually carried from one place to another is getting deposited. That is one of the main aspects of the aeolian geomorphology. So some features, if suppose you are studying the dunes that are there, or any kind of sandy deposits that are present. So how can you distinguish it from say any other kind of natural agent which has caused it? So you will mostly find irregular cross bedding. So cross bedding is actually where the beds, okay, say layers of sands are first being deposited in this kind of orientation, okay. But with time, if the wind direction has changed in at a different angle, so you can see that now the sand has got deposited at this orientation, okay. So the change in the angle of the the deposition of the material over here, this is actually called cross bed. So the beds are actually crossing each other. It can also happen if the wind direction totally changes, okay. So you will have irregular crossing, cross bedding, as in the, since wind is very prone to frequent changes in its direction, uh, you will find that there is no regular intervals of this cross bedding. So this is one important feature that we can find when we are trying to study wind or aeolian landforms. Then mostly they can be gently dipping, steep and orienting in different directions, as we saw. And the particles that are actually forming these the sediments that are forming these depositional landforms range within the diameter that is actually associated with the sand particle size, okay. So these are rounded, well rounded, as in the sediments itself are actually not that rough in its on its surface, okay. So mostly they will not have any edges, they will be mostly rounder in nature, because they actually they are transported over very large distances, and they are also well polished, as we saw that abrasion plays a very important role when we are trying to study the geomorphic processes by wind. So, some examples of depositional landforms are ripples, sand dunes. Sand dunes can be free or anchor types. You will see how they are: ergs, sand sheets, sand shadows, lures. So, from these mostly we will try to see sand dunes. These are the most important, kind of the landforms that we see associated with wind aeolian geomorphology. So, these are some types of dunes. Okay, so these are the diagrams. So, you have blowout dunes, Marchand dunes, parabolic, barachnoid, dome and transverse. So, we will try to see some of the dunes, these type of dunes, how they are formed and how they differ from each other. So, as we talked about one of the example sand ripples. Okay, so this is when larger sand grains are actually accumulating together and forming ridges, and the smaller sized sediments are transported away. So, these actually are perpendicular to the wind direction. So, the wind direction is in this, like suppose the wind is blowing from the left to the right, and these ripples are actually formed perpendicular to the wind direction. Okay. Now, sand ripples, as we said, they have a larger grain, they are made up of larger grains. Ripples are smaller sand waves that are actually built or that you can see on top of sand dunes. Okay, so they are just smaller in dimension, and they move as per the changes in the wind velocity itself, and the wavelength is only up to about 1 meter or so. Okay. And as I said, they can move, disappear and reform during changes in the wind velocity and the direction. Then we have wind blown dust. So, this is again the transportation of sand, but it is kind of in a it forms in like a dust storm, and it does not travel very long distances, it is localized, but the sand, if it is suspended in the wind, it can form into the wind blown dust. Then you have the most important aeolian geomorphic feature. So, they are called dunes. So, these are obviously the classic aeolian landforms that we study. They can be stable, as in they may not move at larger rates, but there are some dunes which do advance with time. It depends on the transport of the sediment that are the sands that are actually creating the dunes. So, usually they form first in like small mounds, and then with time the sand actually gets built on top of this, and what you are left with is actually a gently dipping side of the dune, and there is a steeper side on the other part of the dune. Okay, so we will do this in more detail. So, this is just an example. So, there is no symmetry as such. So, you will not find very symmetric sand dunes. You will find asymmetric sand dunes. Okay, so asymmetry is always present with respect to dunes. Symmetry not present when we are considering aeolian dunes. Okay, so you have gently windward slope. Okay, so this is your windward slope, and this is your leeward slip face. Okay, so this slip face has an angle. Okay, as we saw in the previous, so you can have free dunes and anchor dunes. So, in for free dunes, actually there is nothing constraining the extent of the dunes that are being formed. So, mostly all kind of parallel or linear dunes can be called as free dunes, and anchor dunes are actually those which are dependent or which are controlled by the prevailing topography or vegetation that is present. So, if the dune has started forming due to the small cluster of vegetation that is present. So, the dune that will form over there actually will not travel, cannot advance from one place to another because of the presence of the vegetation, and the dune will form around the vegetation. Okay. So, those are called anchor dunes. So, mostly you will have coastal dunes, parabolic dunes. So, these are some common examples of anchor dunes. So, over here we can see that this is a example of Barchan dune, then this is a parabolic dune, this is a transverse dune, and this is a longitudinal dune. So, from this we can say that Barchan is actually an example of it can be if there is nothing that is anchoring it. So, Barchan dune can be anchoring or a free dune. Okay, parabolic dune is mostly an anchored dune. Okay, transverse dune is mostly a free dune, and longitudinal dunes are also free in free dunes. Okay. Now we will see how the sand dunes are forming and what are the different geometric terms that are associated with it. So, the slope which is actually facing the wind. Okay, so where the wind is actually the direction of the wind is actually striking the slope. So, this is the windward slope. Okay, and the slope, okay, and the slope which is actually in the which is not facing the wind. Okay, opposite to the direction of the wind is actually the leeward slope. Usually the leeward slope has a steep slip face. Okay, this can also be called as slip face. Okay, so mostly the angle is between 30 to 34, and this part is actually the crest. Okay, so the sand actually builds on the leeward side, sorry, on the windward side. Okay, so the sand actually is deposited and also moving over the windward side. You can see over here that first there was just a mound. Okay, so the sand started forming in terms of mound. Okay, and then slowly the sand actually starts building up over the windward side. Okay, and with time, okay, if the wind velocity changes, okay, it does not get the deposition does not happen anymore, but the wind velocity changes, it has increased. So, what will happen is the sand, this part, okay, so the sand over here will start getting eroded and transported. Okay, so this is how you have advancing dunes. Okay, so the free dunes that is moving, it is because of that. Now you can see that the sand was carried forward, okay, and it starts depositing on the slip face, on the previous slip face that was created. Okay, so the sand deposited, uh, the sand that is eroded here is actually getting deposited in the slip face area, and now you can see how the crest has moved from this place to this point. Okay, so this was the previous crest, and now the crest has moved over here. So, this is the how sand dunes advance. Okay, so for this you need changing of the wind velocity or the speed. Okay, but the direction of the wind is not changed. The direction remains from the left side to the right side. So, Barshan dunes are actually kind of the textbook sort of examples of sand dunes. So, these are asymmetric, and you can see that these are actually sort of crescent shaped, And again, if this is a wind direction, the crest is actually developed perpendicular to the wind direction. Okay, you can see how the wind is actually moving. These are obviously isolated and they can freely migrate from this point to another. As you can, if the wind the speed changes, this sand will get eroded and then this will get deposited over here, and the crest changes from here to here. Okay, so this can happen. And the windward slope is mostly it's longer and gentler in nature, and the leeward side is short and steep. So they can have great heights around 20 to 30 meters, and the width, they can be much wider in terms of its lateral expanse also. So as you can see, the dune, if it is moving, if it can migrate, so the dune movement will also be in the direction of the wind that is flowing. Now we come to transverse dunes. So these are again linear dunes, and these usually look like ridges of sands, and again the crest is perpendicular to the wind direction, and these may evolve in bar chance if these uh, there is a change in the kind of the there is a variation of the in the speed of the wind from one place, from in the lateral way. So they can turn into bar chance, and mostly these are occurring in beaches, floodplains, and so places where you have sandy bedrock. Okay, so transverse dunes are one type of sand dune. We also have domes. So they don't have really slip faces, but they are kind of collection of sands in dome shape. Then you have reversing dunes. So this can happen if the wind direction, there is wind coming from the opposite side also. And so what happens is the crest of the reverse dunes is actually it starts forming a sinuous kind of a nature, you can see over here. So initially the dunes were forming due to this prevailing wind direction. Okay, so this was the crest, as you can see over here, but the wind direction has reversed, and now this, which was initially in this manner, okay, has now formed a sinuous or a curved kind of crest in response to the reversing in the direction of the dunes, of the wind direction, sorry. Then we have longitudinal dunes. So the the unique feature of these dunes is that the crest of the dunes are actually in the direction of the wind. For longitudinal as well as Barchan, we saw that the crest is essentially perpendicular to the wind direction, but in longitudinal dunes, the crest. Okay, yeah. So the crest is forming in the direction or parallel to the wind direction. Okay, and these are mostly very strong persistent winds. These can also be called safes. Okay, so mostly they appear, to have kind of sharp crests, and they form in dry tropical deserts, and they can be separated by lag gravel are coarser sediments. So one sieve can be separated from the other sieve by different kind of lag deposits in between. Then we have star dunes. Now star dunes are essentially developed when the wind direction changes a lot in a desert area. Okay, and you can see that usually in Barchan dunes, Okay, these are called your wings, or the arms of the dunes. These I draw here. Okay, so these are called wings, or the arms of the dunes. Okay, so in star dune you will see that there are just not two wings or arms. You can have several kind of arms of the dune, and they are all irregularly shaped, and they can grow in height, which is more than all the other dunes, because the sediment supply, there is no regularity in the sediment supply that is being brought in this in these areas. Now we will see what are parabolic dunes. Parabolic dunes is mostly because the dunes actually have a parabolic shape. So if this is similar to the Barchan dunes, but the Barchan dunes we saw that the wings are not generally they are not increasing in length, but for parabolic dunes the wings or the arms of the dunes are much longer. So usually these are anchored dunes because the sand cannot move uh, a lot, in it cannot advance, or the dune cannot move from one place to another. So the crest, essentially this crest part cannot move due to the presence of the vegetation. So only the wings or the arms of the dunes are free to move, so only they advance forward, and hence you have longer shaped wings of the parabolic dunes. Okay, so as there are vegetation which is which has a role in the forming of parabolic dunes, if we can assume that these actually do not form in totally arid regions. You need some humidity, so they can form in subhumid and semi-arid regions, and they can usually originate from blowouts, as in the sand is this area is actually where the finer sediments have been blown away from. Okay, and since the vegetation over here is holding on to the sand over here, so what happens is that this actually ends up taking a dune geometry, and the wings of the parabolic dunes with the continuous blowing of the winds actually grows, and then they take up this parabolic shape. And see, the head of the dune is where the vegetation is present, and the downwind part of the dunes are actually blown out, and then they can form into blowouts. Now the next one is called Nabka. So these are kind of hammocky in nature, and most of the crests of these dunes are actually uh, held on by the vegetation that is present, and these are plant anchored dune, and these are mostly, again this can also form in semi arid environments. Okay, so now we will see how, as we know that Kutch, the Ran of Kutch, is actually kind of an arid area. So in Kutch there is a interplay of both your tectonic geomorphology and the previously formed aeolian geomorphic features also. And Kutch is one area where you have intra-plate seismic activity. Okay, so if you remember in the, I think the second week of our course content, we had talked about plate boundaries. Okay, so plate boundaries, so either you have divergent plate boundaries, or you have converging plate boundaries, or you have transform plate boundaries. So these are between two plates. Okay, so this boundary, now because of either diversion, conversion, or transform plate boundaries, so any of these movements can cause seismic activities. Okay, we know this. This is how you have earthquakes, and then how we study the seismic waves that are developed due to these seismic activities. Now, sometimes there are seismic activities generating within a plate. Okay, within a plate. So these seismic activities that are say occurring within the plate A itself are called intraplate seismic activities. And usually these are rare in nature, because as we saw that these are ways how stress can transfer from one place, from one plate to another, and the collision or the diversion, the movement itself can cause disturbances in this region. So having an intraplate seismic activity is less known, and we will see what are the differences between interplate and intraplate. So in Kutch region, we have got evidences of intraplate seismic activity. And as we saw, why are we calling it an intraplate region, is because it actually lies 300 to 400 kilometer away from the plate boundary between Indian and the Eurasian plate. Okay, so as you know, so this is where you can this area you can say is the plate boundary between the Eurasian plate and the Indian plate, and the Kutch area is actually situated here. So the distance is much greater. So any activity from here, okay, so logically we will we can think that there shouldn't be no effect in this area, but there are seismic activities that have been recorded in the Kutch region. And so the current tectonics that are actually happening over here are are far off effects of this plate boundary tectonics, the any tectonic processes that are happening over there. Okay, so if we try to distinguish between an interplate and intraplate earthquakes or seismic activity, so the interplate occurs at a plate boundary between two plates, continental ocean or continental or oceanic plates. Whereas intraplate earthquakes, if you are only talking about earthquakes, so these occur in the interior of the tectonic plate. Mostly these can occur in areas which are very much farther away from the plate boundaries itself. The recurrence time of the plate of the interplate boundaries is less. Recurrence time, as in the interval between two earthquake events that are taking place at the plate boundary, is much it's lesser. Okay, so the frequency is more. Okay, so this means the frequency of earthquakes at this in interplate regions is high, and the frequency of the earthquakes in intraplate regions is actually low. So interplate earthquakes can be easily recognized on surface because it's between two plate boundaries, and you get features like either in oceanic you have mid-ocean ridges, and if it's converging boundaries between two continents, you have mountains. So we know that these areas are the hotspots for any interplate seismic activity. But in the case of intraplate earthquakes, it is not easily recognized at the surface, because mostly the the region where the activity is actually happening, or kind of faults which are actually responsible for these earthquakes, are can be buried under several layers of the surface of surface material. And because the frequency is low of the intraplate earthquakes, and as well as the recurrence time interval is much longer, it is difficult to assess the effect of these intraplate earthquakes on the surface. So the fault which is responsible for intraplate earthquakes may not extend all the way up to the ground level where we are trying to study. So this is one limitation of that we face when we want to study such intraplate earthquake events. And interplate earthquakes release less stress, and they dissipate quickly, because the region between the two plate boundaries is already, mechanically and rheologically weak in nature. So the seismic waves that are being generated by interplate earthquakes can be absorbed by these weaker rocks that are already present between the two plates, between the two plates at the plate boundaries. But for intraplate earthquakes, they release more stress, and the ground motion is actually amplified if there are no weaker rocks present, which can actually absorb the seismic waves that are actually traveling from the point of the point or the focus of the earthquake to the region which is getting affected. So strong rocks, or very hard rocks, actually help in the transmission of the seismic energy over longer distances, and they can be very much hazardous to us, and they cause a lot of destruction. We will see some examples of such earthquakes. So we know about the 2001 Bhuj earthquake. Okay, so when people started studying the 2001 Bhuj earthquake, a lot of studies actually tried to understand any of the past earthquake events that might have, uh, happened in the Kutch region itself. So, in 1819, one of the earthquakes that was recorded uh, of a magnitude of 7.7 to 8.2, and the intensity of this earthquake was also extreme. Okay, so this actually caused two kind of tectonic uh, you can say tectonic displacements in the area which was surrounding the earthquake epicenter. So there was subsidence that had taken place, which actually formed the Sindri Lake, and there was a local zone of uplift also, uh, which actually caused the damming of a river. Okay, so this natural dam was called the Allaban. So over here, if you see, this is the epicenter. Okay, so this was the epicenter over here, and this was the scarp, as we can see over here. So the one part, the one part of the this area. Okay, so the south of this, suppose this was the scarp that was formed. Okay, so this part actually went down, the southern part subsided, which caused the formation of the Sindri Lake, and the northern part of the scarp actually got uplifted, and the river that was flowing uh, in the northern part of this area actually got dammed because of the development of the scarp over here. And the displacement, the on surface displacement that was later on estimated by studies, was around 12 meter, which was actually related to the height of the bund, as well as the amount of the subsidence that was noticed in the south of this scar. Okay, so this La Bund actually became, as you can see over here. Okay, so this is actually the northern or northeastern part, and this is the southwestern part. So the subsidence that was caused over here actually created the lake, and this scarp formed actually the it dammed the river flow, and there was no more water that was flowing in the northern part. So this is kind of an effect of the tectonic geomorphology, what we had studied. So as we already seen, so the natural dam actually formed across the Puran river, and this actually stopped the flow from the upstream to the downstream area, and so this is one of the, you can say, changes, a big dynamic change that we see in the landscape that is caused due to tectonic activities. So intraplate tectonic activities actually cause such drastic changes on top of the surface in the area, and there is no other say control over the geomorphology now. Now the topography over here has changed for uh, it will not change back to its original form anytime soon, or maybe it will never ever change. So tectonic geomorphic processes, or tectonics itself, can cause irreversible changes in the geomorphic kind of disposition of an area. And as we said that the later earthquakes, one of the most famous earthquakes that have happened, uh, with respect to the Kutch area, is the 2001 Bhuj earthquake. What people have said, that the changes that in the stress that is contained by the plate, okay, because of the 1819 earthquake, was sufficient to trigger the earthquake in the 2000 in the January of 2001. And obviously there was another earthquake in 1956 called the Anjar earthquake, and this was actually kind of a uh, due reverse faulting that was caused by the 1819 run of Kutch earthquake. So you can see around say about 200 years old earthquake can have significant after effects in a place. So this is mostly seen, you can see that the recurrence interval is much longer compared to what we see when we consider San Andreas fault. Okay, San Andreas fault is a plate boundary, it's a transform fault boundary. So over there we find very recurrent earthquake events. Okay, so we read about it in the recent research papers as well as news. But when it comes to the Kutch area, you can see that the time interval between two subsequent earthquake events is actually pretty high. So the one earthquake which had occurred around 200 years ago has very long term effects, and it actually causes long term changes in the topographic and the tectonic setup of the area, and it can cause further earthquakes. So this kind of raises the question, if even 1819 run of Kutch earthquake was an effect, or was the after effect of some other prehistoric earthquake that had occurred in this area. Okay, so this is when we try to study all the different earthquakes that have taken place in one area, and we try to map the changes that have been caused by a certain earthquake, and we try to relate it to the previous topography as well as the changes that had happened because of any historic earthquakes that have happened over there. So in terms of the 2001 Gujarat earthquake, okay, so it was extremely intense earthquake event that had taken place in the Ran of Kutch area in Gujarat, and it was again an intraplate earthquake, and you can see that the depth, it is pretty deep in nature, and because the uh, the substrate over there, or the the rocks that are present over there has aided in the transmission of the seismic waves that were generated because of the earthquake, and it traveled for longer distances, and it caused very large destructive effects. So the 2001 Gujarat earthquake was, when it was studied, it was found out that the cause of this earthquake was due to the movement on a previously unknown fault, okay, unknown south dipping fault. which is actually trending parallel to the rift basin structures that are already present over there. Okay. So you can see over here all the different epicenters and the of the different earthquakes that have formed. So to the 2001 epicenter is obviously at a distance from the 1819 as well as the 1956 earthquake over here. Okay, so this earthquake in itself was obviously the stress was released due to the movement along an unknown fault. Now this fault was actually hidden. Okay, so this fault was not seen on the surface. It was not recognized on the surface of the locality. It was actually hidden, and because there were no major surface ruptures that were associated with this earthquake event, what they categorized or classified this kind of an earthquake as a blind thrust earthquake. Okay, so mostly there was a lateral spreading of the stress release. Okay, and this was said to be along a strike slip fault that was observed at Bharodia and Manfara. Okay, so this. So they actually kind of measured the displacement of certain points, in the vicinity of the earthquake, and that's when they realized how the displacement had actually occurred, and then they classified it as a thrust related earthquake. But since they could not see any surface manifestation of this rupture, they called it a blind thrust earthquake. Okay, so now as I said that this area has seen earthquakes at very large, longer recurrence time intervals. So this raised the question if any, this area was also the, um, you know, the settlement area of the Indus Valley civilization. Okay, so part of the ancient civilizations were actually, this area was said to be the home of these civilization. One of the most important one is the Harappan civilization, and as we know that with studies, archaeological studies that have been carried out previously, these civilizations faced their end due to some sort of very large natural disaster, and it was also seen that there were changes in their kind of uh, architectural structures or construction sites. They differed from one period to the another. So this actually kind of raised the question that if Harappan civilization was in this area was actually affected by any prehistoric earthquakes, and if the earthquake occurred, what were the changes that were seen, and how the people actually re-established or rebuilt their civilization after that earthquake. So this intraplate Kutch region has, with documentation and historic studies, have actually scientists have found that around 2700 BC there was a Dholavira earthquake. Then after that there is obviously 1819 Alaband earthquake, 1956 Anjar earthquake, 2001 Bhuj earthquake, and the 2011 sorry, these are the references. So the major earthquakes that have been recorded or studied in this area is the 2700 BC one, 1819, 1956, and the 2001 earthquake. So now the hypothesis that was given by the authors or the researchers was that the decline of Harappan civilization was most probably caused by the natural calamities which were associated with floods and earthquakes. So one when people started try to study the settlement and the the orientation and the geometry of the major settlements in the world, so that's where the correlation was kind of established, and earthquake hazard seemed to be one of the reasons why destruction of such settlements had happened. So the 1819 event caused the formation of the Alaban Scarp, as we had seen, and some features like paleoliquification and study of the excavation sites that were carried out actually kind of gave us a picture that an earthquake in the historic times actually caused the burial of some settlements, and it was due to the 1819 earthquake itself could have been a long term after effect of the prehistoric the earthquake event also. So that's what they said. So the liquefaction features that were documented in the epicentral zone of the 2001 Bhuj earthquake actually suggested that the Kutch region was hit by a similar magnitude earthquake event around 1000 years ago too. Okay, so that is what we tried to see that prehistoric earthquakes in itself, if it is an intraplate region, they can have uh, after even thousands of years of the original earthquake, maybe you can see the effects or the rupture that was created during that time is actually kind of buried under layers of later on layers of deposition, and you don't know, you if there is no surface manifestation, it is very difficult to point out the area which is actually prone to future earthquake events also. So over here what they tried to study with respect to Dholavira, so which was actually present around 2600 to 1600 BCE, and it is you can say that this area is actually currently situated 60 km north of the epicenter associated with the 2001 Bhuj earthquake. So what the archaeological records have suggested that a major earthquake did hit the Dholavira area at around 2200 BC, and what was the what were the evidences that actually supported this were the displaced vertical walls. So if the walls initially were constructed like this, so after the earthquake there would be a displacement either at an angle or a vertical. So if so you can see that which part of the land has actually was upthrown and which was downthrown. So this vertical displacement in the walls can signify the occurrence of an earthquake event. Then you have bulging and tilting of walls and columns. So these are all the consequences of different the effects of stress release during earthquake, and rotated pillars and large scale repairs that were undertaken after the occurrence of these earthquake events. Then this is the archaeological findings. How can we try to study these things with respect to geomorphic features, is that there is an increase in river gradient. When we were seeing the tectonic geomorphology, we saw if during the development of a scarp, there could be an increase in the slope along the scarp's face, and due to that there would be an increase in the river gradient, or there is a there is a displacement of the river, the course of the river also. Then obviously development of false scarps as we see, and then offset that we were talking about, offset of drainages and the river courses. Then the formation of strath terraces, and as well as ponding within river channel, if the scarp is developed and the flow of the stream is kind of obstructed, so there could be ponding, or if one part of the river gets separated from the say if it's a meandering river and one part of the meander is cut off from the main channel, so you could have a ponding of the river that is present over there due to the fault plane. So and some other kind of features that are that can help you in understanding um, uh, the study of the fault that is causing the earthquake events is evidences of fallen debris. Then archaeological studies was like saying tilting of community door, bulging and slumping of fortification walls. So these were all the observations that led to the understanding and hypothesizing that um, an earthquake event actually hit the Dholavira site about 2200 BC, and this could be this was one of the major events that caused the decline in the Harappan civilization, as was as the settlements in the Dholavira was studied. So one another feature that is associated with paleoseismic studies or historic earthquake studies is sand blows. Okay, so during earthquake what can happen is like the sand that is buried below layers of sediments or rocks can actually liquefy, and this actually because of the increased water pressure, this liquefied sand starts behaving like a liquid, and it tries to erupt onto the ground from say fissures or openings. Okay, so a slurry of sand and water is forced on the ground surface, and these are called sand blows. Now studying sand blows is helpful in a way that if the age of the material below the sand blow can be dated, okay, and the sand blow is kind of a a feature that is only associated with the earthquake event. So since this does not have any material that you can date very easily, so if you can date the material below the sand blow, that means that the earthquake has occurred after the date at which the material below the sand blow was dated. Okay, but if the sand blow is buried under material that can be dated, then we can say that the earthquake event which actually formed the sand blow had occurred before the deposition of the dated material. Okay, so this is how sand blows paleoseismologists as well as in archaeological studies, if they study sand blows, this can help us in trying to date the different earthquake events and give their ages. So paleoseismic studies, paleoseismologic, trenching is one of the tools that is important to understand the paleo earthquakes, historic earthquakes, and studying these, previous earthquake events can help us predict any the occurrences of the present as well as the future earthquake effects. Okay, and as well as the faults which are present, we can try to predict what sort of movement will happen and which area is more prone to the after effects of the earthquake event if it takes place. Okay, so trenching is actually they dig out one kind of a rectangular portion. Okay, so mostly this is carried out in areas which have compacted but not consolidated sediment areas, where you can find the different layerings as well as the displacement between the layers, and this is useful in studying in active fault studies. Okay, so the trenching actually exposes the stratigraphic and structural relationship of buried modern deposits. Okay, because modern deposits like the few thousand years ago deposits, if they are there, or few hundreds of years ago, So these are not very compacted, you can easily dig through them and you can make trenches, and this helps you in studying active fault or fault segments, and to understand the location and the magnitude of future earthquakes in the study region. And paleoseismic studies in itself helps us in assessing the seismic risk, as well as kind of provide natural disaster management efforts. So you can see the trenching, as we said, it can give you an understanding of the rupture geometry. Okay. So trenching can give you, or it can, the face of the trench wall can actually expose the rupture geometry, as well as the style of faulting, like if it's a normal fault or a thrust fault, and the stratigraphy and the complete depositional history, and it can help us in understanding at what was the age of the earthquake event that had taken place, and if there is any buried displaced feature. So for example, over here this was the picture taken of the trench wall, and this, actually they have already annotated the different layers that you can see over here. So you can see that this fault is present over here. Okay. And so when this fault had actually happened, so all the material that is deposited on top of the fault has deposited after the earthquake event, obviously. So if you can date the material, say this charcoal layer material over here, or this sand and silt material over here, then you can date the kind of the age when the fault actually when the displacement about the fault had actually taken place. So to reveal the slip history, we need multiple trenches which are closely placed, hopefully along the fault line that is present, and successive exposures are, as I said, orthogonally present, orthogonally cut to the fault zone. And two fault parallel trenches can also help us in identifying the offset of the features. Okay, so maybe one part was not disturbed and one part was disturbed, so we can compare them and try to see what was the direction of the slip, and try to find the slip history that is associated with the fault that we are trying to study. So that is it for all the different geomorphological aspects of different natural agents, as well as the tectonic geomorphology, which is a combination of tectonic processes as well as other natural agent related geomorphic processes. So we are done with all the weekly content of this course. So if you have any doubts on about any of the lectures that have been done till now as well as today, you can put them in the discussion forum, and we will try to answer them. And most probably we will hold a revision session. The NPTEL team will make the announcement for it, uh, uh, and I will also give the details for that session on the discussion forum also. So hopefully this has helped you to revise and have a more concise understanding of geomorphic processes on a whole, and hopefully this has helped you also in solving your assignments. And so thank you so much for this opportunity, and hopefully I will see you all in the revision revision session. So thank you, and this will be uploaded as per the normal schedule. The NPTEL team will update it. Thank you so much.